Okay, if we want to write the integral, we've seen that the integral is the area under the curve, or net area between the curve and the x-axis, technically speaking. But using the definition of these, well, as you'll see, it gets complicated pretty quickly when we're using the definition of the derivative to write it out. And so I think there's a couple on the homework, so let me show you how this works, because we haven't really technically done one yet. All right, so our definition of integral, definite integral, is the definite integral a to b f of x dx equals the limit as n goes to infinity of the summation I equals 1 to n f of x sub I star times delta x, where delta x is b minus a over n. Now, so so what I want to do is I want to take this and write it like that. That's the idea. Now, to make it a little easier on ourselves here, this x sub I star, that could be any left-hand endpoints, right-hand endpoints, midpoints. And so the ones that they'll have us do, I believe, the one we'll do another one later too, but we'll use the right-hand endpoints, okay? So if we use right-hand endpoints, which I believe is what they'll have you do, it's just limit as n goes to infinity, summation I equals 1 to n, f of just x of I times delta x. So that's what we're going to shoot for here on this one. Instead of doing midpoints or left-hand endpoints or anything like that. We'll just use right-hand endpoints. Okay. All right, so what do we got here? Well, first of all, let's just figure out a few things. This, of course, sine of x is our f of x. And so I'll be doing f of x sub I of the sine of x. And so that is one thing we could put in here. All that stays the same. But it's f of x sub I. Well, f of x is sine of x, and so f of x sub I would be sine of x sub I, right? Times, that's the first thing we can do is say, well, my f of x is sine of x, and so f of x sub I would be sine of x sub I. Would be there? And what about this delta x? Well, delta x, we know is b minus a over n. And so the delta x in this case, we can simplify it, if you will, a little bit. What's my b and my a? Well, the endpoints are the b and the a, right? This is a, this is b. And so b minus a would be 5 minus 0. And then n, I don't know, n ultimately goes to infinity, but I don't have a value for n like, normally would say four rectangles or 4 subintervals, but in this case, we don't even know, okay? Because we're going to run into infinity ultimately anyway. But anyway, all we can say delta x is 5 over n. And so times delta, that's f of x sub I, times delta of x. Okay. Now, that's a good start, but they want us to do a little bit more here. Let's figure out, is there something maybe that I could use in place of x of I there, instead of saying x of I? Is there something I could write in this place? Well, let's just start out by writing writing out the x of I. You know, x of 0, start there, that's just an a, which is 0. All right, so what would x of 1 be then? X of 1 is just then taking x0 and adding delta x to it. So x of 1 would be 0 plus my delta x. So it'd be 0 plus 5 over n. It's just 5 over n. So x1 would be 5 over n. What would be x of 2? Well, x of 2 is x of 1 plus another delta x. It's 10 over n. X of 3, then, we would take the 10 over n and add another delta x, 5 over n. 15 over n. And on we could go. I think we maybe see a pattern here. X of 4, 20 over n. X of 5, 25 over n, right? So what would x of I in general be? Well, we definitely know the denominator is n, right? Because each one of these, we've got a denominator of n. The question is, what's the numerator, the top? Well, just look at it. This is 5 over n for x1. X of 2 is 10 over n. X of 3 is 15 over n. So what are these numerators? How can we get these numerators by using the I there? Well, these are just multiples of 5. And so the first one is 5, the second one is 10, the third one is 15. So what's the ith one? It's 5 times I, isn't it? Right? You just take whatever this is and multiply it by 5. 5 times 1 gives me 1, not 5. 2 times 5 gives me 10. 3 times 5 gives me 15. 4 times 5 would give me 20. So whatever the I is, take it and multiply it by 5, and that's your x of I. Well, that's what they want me to do then. I figured out that the x of I is 5i over n, so my final answer here, since I don't have to evaluate it, would be all this, didn't leave myself enough room, and then plug in that x of I to be 5i over n. That would be my answer, for the answer that they would want. Writing as a limit of Riemann sums using the definition, that's what we want. Okay. So yeah, like you can see there, that's kind of complicated. We've done some limits, but we haven't done any limits like that. That's a pretty complicated limit. And most of these integrals, the limit definition is very complicated, but some good news coming. All right. So that's one thing else they'll have you do. Like I said, you don't have to evaluate it, just get it set up like that. Now, a couple other notes. Let's talk about the properties here. A couple of properties of integrals. We've already mentioned a couple of them, but properties of integrals. First one is, we're used to going, we usually say let's go from A to B. Well, what if we go backwards, if you will, and go B to A? Well, yeah, usually we say, the A is the smaller one. And so from A to B, that's what we've been talking about. Well, what if we go from the lower limit B to the upper limit A? How's that related to the A to B f of x dx? Well, it's it's tied in, the definition here of, just had it written down, it's that limit as n goes to infinity summation I equals 1 to n, f of x of I or star, delta x, or delta x is b minus a over n. Well, what happens here is that's if you go in A to B. Here I'm going B to A. So doesn't that change those around for delta x? Now delta x is A. For that, it would be delta x equals A minus B over A. Well, long story short, those are related. Those two delta x's are related. They're just the opposite signs of one another. If b minus a over n is, say it's 0.25, then a minus b over n would be negative 0.25. You with me there? It's just opposite signs. Because you switch a and b around, right? Well, if this is delta, that's just going to make that a negative. If we look at it that way, b minus a over n is positive, then that's going to make that negative, which makes everything negative, negates everything. So that, long story short, what it does is it just makes the integral the negative of what it would have been. Because you're going, another way, instead of going from A to B, we're going B to A, so we're going backwards, so to speak. So it negates it. A couple ways you can see it, or think about it. So, just to give examples, all right. So if 0 to 5 f of x is, say, 7.25, then the integral from 5 to 0, f of x dx, what would that be? Which is negative 7.25. Or if that's negative, then that would be a positive. I mean, it doesn't have to go positive, negative, it can be negative, positive. See what we're saying? So changing those limits makes it negate what. All right, so that's one. Number two, we should have started with this one. A little easier. Getting back to the definition or what the integral gives me, the integral gives me that area from A to B, right? Area under the curve, or net area drops below the x-axis. That's what the integral gives me. Well, what if my lower limit's A and my upper limit's A? Basically, I didn't go anywhere as far as the x is concerned, right? I'm just talking about this curve, but I'm going from A and I don't go anywhere. Well, if this integral is the area, what area is underneath there? Well, you didn't go anywhere. You don't have any area, right? You got zero area under that. With me there? So if your limits don't move, you got zero area. We talked about this one a little bit last time, the third one. A to B, f of x plus g of x. Yeah, those additions, those are really nice. And again, it gets back to the definition. I mean, if I put this into this definition here, so now my function is actually two functions. Well, it's still addition, and this is addition. I think it's hopefully clear there that I can separate those and make those two separate limits because I'm just adding. Yeah, this is just adding those terms. So I have this term plus this term, x1, g of x1, f of x1, g of x1, then I have f of x2 plus g of x2, then I have plus f of x3 plus g of x3. So I can reorder those because, you know, that would multiply in. Anyway, if you wrote it all out, yeah, you can separate those into two separate limits. Well, that's the integral for f of x, right? And that's the integral for g of x. Yeah, so you can separate them like that. You can do that. And that's a big deal because it's not at all the same for every operation between f and g. It is the same. I guess you could call this number 4. You can do the same thing for minus. Ditto. Okay. You can reorder them like that. Now, those are properties of integrals. So you can separate, I didn't write it out here. So what we're saying is you can separate those into two separate integrals. Same thing here. You can separate those into two separate intervals. Or think about them. Don't necessarily write them usually out, but you can do addition and subtraction. You can do the integrals separately. Basically what it means. Now, that's, you maybe say, duh, okay, that's right. No problem there. However, here's some non-properties. These don't work. This is really kind of special. You cannot separate times, and that's what kind of makes these integrals so tricky, complicated, if you will. When I've got two things multiplied, it doesn't work. You can't do integrals separately. When they're times, two functions of x, you can't do that with times. Neither can you do it with divides. It does not equal the integral of the top f of x divided by the integral, in general, right? The integral of g of x. So these two are special. They're really, really nice. We like it when we have pluses and minuses between in our functions because we can just do those separately. They're really easy integrals. They're eventually what we talk about. You can't do it with times and divide though. That's what makes these integrals so fairly complicated. And we talk a lot about what we do when we have multiplication and division in intervals in the days to come. And future calc, if you take calc 2 and calc 3 and others, we talk about those extensively. So yeah, we'll do some of those, a lot of those. All right, a couple others. One more, probably five. I don't think these are probably not the same numbers as they have in the book, but all right. So number 5 property, integral a to b c times f of x dx. Now, all right. So I just said that about times. You can't separate those up. Well, if you just have a constant times a function, you can bring that out as one way you can think of it. But that's kind of nice. You know, if you know, I think this is kind of maybe like to have. So if I have 1 to 6 f of x dx is 1.2. What's the integral 1 to 6, 5 f of x dx? Well, you can do that. If you just have a constant times your function, you can think of that as 5 times 1 to 6 f of x dx. And then we know that's 1.2, so it's 5 times 1.2, since that's the value of that integral. You can do that sort of multiplication if it's just a constant. That's 6. So 6. Anyway, now here's another one. Last one I'll go over. We'll use this one a little bit. There is sometimes it'll be nice if we can break up an integral. We're talking about a to b, and I'll give you a good example of one where we have an absolute value, maybe, which means we have a corner. All right, so let's say we're trying to evaluate this a to b integral, which is this area here. I'm trying to figure out that area there. Well, corners again in our graph, those are problems. You know, there are problems with derivatives and the problems for the integrals too. But so it's going to be nice here if I can break this up at this corner here, C. I mean, it doesn't have to be a corner necessarily, but that's a good example of one where we would. So if I could break this up at C, I could probably figure this out a little better. Well, it turns out we can do that, so now we can just do the integral from a to c, f of x dx, and add to that the integral from c to b. You see what I'm saying? And add those two together. Isn't that going to be true? Because what is this? It's the area under the curve from a to b. Well, that would be this area, that would be this area, so those two things are the same. Makes sense. Hopefully makes sense. Like I said, it doesn't have to be corners, it can be any. So we'll go A to B. I can pick any C out here. Doesn't even have to be in the middle. It's the same idea. That would be this area, that would be this area. It doesn't have to be a corner. That's a good example of one that it works well for. In either case, you're going to get that integral from a to b covered with those. So you can pick any c out. Usually it's in between a and b. All right. So those are a few properties, and we'll utilize some of them as we go along here.